course, vary from day to day. But we're going to think about setting the air pollution level, which is a random variable written as this big X, equal to some specific value, which we'll call small x. And then given that we've set the air pollution level to that value of small x, then we want to think about what is the expectation of y. So on average, how many hospitalizations do we expect to observe on that day? And then we can think about manipulating like what the small xi is. So we could set little x to be a very low value, which means that it's a low air pollution day. And we think about the average number of hospitalizations we might expect to see on that day. And then we could also think about manipulating xi, little xi, so that it's like a high air pollution day, it's a very high level. And then think about what the average number of hospitalizations we might observe on a day with high air pollution levels is. So that's going to indicate to us that our expectation of y may change depending on the particular value of xi, so whatever particular value xi realizes there. So you can imagine if we had this data set, then we could visually represent the relationship between these two variables, right? So we could use a scatter plot to visualize the relationship between air pollution and hospitalizations. So what we have here is I made up a data set in Stata. This is not actual hospitalization data and not actual air pollution data, but I just generated some. And on the x-axis, you have the value of x, which we've said is air pollution. On the y-axis, you have the number of hospitalizations. And each dot is basically a separate data point. So you can think of each dot as being a separate day that we've observed here. And you can see that given the way that the data looks, it seems like there's a pretty clear relationship between pollution and hospitalizations, in the sense that if you were to kind of like draw a line through the dots or something like that, it would have an upward slope, right? It seems like as air pollution increases, hospitalizations tend to get somewhat higher. So what if we wanted to formally summarize that relationship, rather than just kind of waving our hands and saying, look, it looks like there's kind of like a positive upward slope here? What if we wanted to summarize it? So the way that we could think about summarizing the relationship is to basically calculate how the average number of hospitalizations changes as you move across the x-axis there. So as pollution levels increase, how does the average number of hospitalizations change? So if we wanted to do that, we would sort of proceed in like several steps, right? So the figure that I showed you before, on the x-axis, like the number or the air pollution level was basically ranging from I think like 1 to 6 or something like that. And so you start at the left-hand side of that figure and you calculate the average number of hospitalizations on days when the pollution levels are near 1.0. And then you just kind of ratchet up, right? You say, okay, well now I'm going to next calculate the average number of hospitalizations on days when pollution levels are 1.1, then when they're near 1.2, and so forth.
So the values that you give them, like, are they discrete? Like you just have like one thing for the
So let me go. Okay, so I'll answer that question in like 2 seconds. So first I just want to say, so we're going to continue doing this procedure over the entire range of air pollution levels that we observe in the data. And the answer to the question is that no, I did not give them discrete values. I just wanted to make sure that I in fact did not do that. I didn't think that. But so you can see that, I mean here, it's not the case that we just set air pollution levels at 1, 2, 3, 4, 5, or 6, right? There's intermediate values here because this data point is at like 1.25 or something. This one's at like 1.98 and so forth. So if we do the procedure that I just described, what you're going to see is the function that's generated or that's presented or plotted by that red line right there. Right? So what the red line is doing is that it's saying, okay, I'm going to start at 1.0. I'm going to take the average of data points, the average number of hospitalizations for data points that are near this value of 1.0. Then maybe I'll move up to like 1.2. I'll take the average for data points that are near average number of hospitalizations for data points that are near 1.2 air pollution level. Go up to 1.5, do the same thing. Go up to 1.7, do the same thing, and so on. And basically all the way from 1 to 6, calculate like sort of a moving average of how what hospitalization levels are for data points that are near that particular point where I'm trying to calculate the average. Okay, so if we do that, then you end up with this red line. Karen?
So are all the points on the graph or just the representative?
You mean like are all of the data points in the data set plotted in the scatter plot there? Yeah. So this is like the entire data set that you're seeing. Right. This is not a 10,000 observation data set.
So like, I don't understand why average would change the way it does since you're just doing the average with like that line.
Sorry. So what do you mean in terms of at any point? Like let's say let's think about what the red line represents at 2.
Like the first point that you have, like the leftmost point.
Yep.
Why is the average above that point
instead of being right at that point? That's a good question. So the answer is basically that I'm not looking for I'm not looking at the number of hospitalizations for data points that are exactly at this point. So let's say that this point that I'm pointing to right now is like 0.95. If you look in the actual data, it may be that there are no observations where we have an air pollution level that's exactly 0.95, right? Because you can see that like there's sort of gaps here. Like there's this one, and then there's no observations with an air pollution level that's like between here and here until you get over to that next one, right? So it's not going to be the case that I could look and given the amount of data I have, it's not going to be the case that I could look and say I'm only going to use observations that have daily air pollution levels of 0.95. So instead, what I'll do is I'll say I'm going to take the average level of hospitalizations for observations that are within some small radius around 0.95. So it'll be like 0.95 plus or minus 1/10 or something, right? So it'll be like from 0.85 to 1.05. And so then the reason that it's like above that line is because it's taking the average not just of this one, but it's also getting a portion of the second dot that's much higher. And the way that, so to be honest, like the way that this particular estimator works is it actually takes like a weighted average where the distance between the point at which you're trying to compute the average and the actual observations is decreasing, or the weight is decreasing in that distance. So because that second point, which is very high, is further away, it receives a lower weight. That's why it's not just like the average value in between those 2 points, but instead it's like 1/10 of the way in between or something. Okay. So this red line is basically going to show you how the mean of y changes as air pollution levels, which is x, change. And what I plotted actually represents in graphical terms the conditional expectation e of y given x. So now the second exercise that I want you to do is basically, or involves calculating conditional expectation functions. So so I want you to calculate the conditional expectation of y given x is equal to x, where x corresponds to a coin flip of a pair of coins. So x is either going to be equal to 0 or x will be equal to 1. And y corresponds to rolling a 4-sided die if x comes up heads, and then it corresponds to rolling the six-sided die if x comes up tails. So I want you to calculate the conditional expectation function of y given the different values that x can realize. So just do that in like a couple minutes, and then we'll talk about that. And feel free to ask questions or clarify questions too. Well, if they're the same number, then you can say that, but you need to calculate what each of the numbers is.
The answer is in terms of which die number.
Well, the answer is, I mean, so this is, as I said, this is a function of x. So basically, the question is, what does this function look like? Like, what are the two values that this function takes on depending on x? Okay. So I think the hardest part of this question is just like figuring out exactly what it is that's being asked. So group 3, do you guys want to give a step? So we wrote x corresponds to a coin flip. X is going to be equal to 0 if it comes up tails, I guess, and x will be equal to 1 if it comes up heads. So what would then be the expectation of y given x is equal to 0? You're group 3, right? Yep. Excuse me? Yes, that is correct. And then what's the expectation of y given x is equal to 1? So if you... Yep. Okay, so that's it, basically. You've mapped out the conditional expectation function, albeit in a very simple case in which x can only take on two values, which are 0 and 1. So we could also rewrite this, remember. We could say that the expectation of y given x is equal to x is just some function h of x. We're trying to figure out what that function is. And it turns out that h of 0 is equal to 3.5, and h of 1 is equal to 2.5. So the way that I happen to write up this scenario, there's actually a negative relationship between x and y, right? Like as x increases from 0 to 1, y goes down. The reason for that is basically just that, look, you're rolling a smaller die when you flip the coin and it comes up heads than when you flip it and it comes up tails. So when you flip it and it comes up tails, then we're saying, okay, given that x equals 0, so it came up tails, then I'm going to roll a six-sided die. I know the average value of the six-sided die is 3.5 because we already computed that the last time. So that's what the conditional expectation function is when the coin flip comes up tails. Alternatively, when it comes up heads, x is equal to 1, then you just roll a four-sided die, and we know that on average that four-sided die or the faces on four-sided die on average are 2.5. So h of 1, or the conditional expectation of y given x is equal to 1, is equal to 2.5. So there's actually a negative relationship between x and y, the way that we define this particular problem. Obviously. Yeah, so so you've defined the entire function across the support of x, right? So x only takes on two values. That's what makes it so straightforward in this particular case. But if x took on many, many different values, then it would be much more difficult to map out all of the different values, how your expectation of y changes depending on x. Okay, so start reading the notes that I posted, and we'll continue talking about this stuff on Wednesday.